Hi, in this video we're going to look at the force on a charge moving in a magnetic field. So before we saw that a wire carrying current in a magnetic field experiences a force. Well, a current is charge is moving, so if we have a free moving charge in a magnetic field, we'd expect to have a force on that too, and we would see a force happening on a charge moving in a magnetic field. It's governed by another formula. The force depends on the size of the charge, the speed at which it's moving, actually the velocity with which it's moving, and the size of the magnetic field plus the sine of the angle. So it's kind of similar looking to what we had before. As a matter of fact, you can actually show that they're equivalent to each other, which I'm not going to do right now. This also obeys a right-hand rule, just like we had before. And it's basically the same thing. If you got your thumb pointed in the direction of the charge motion this time, that would be the velocity, and the magnetic field is still the directions that your fingers are pointed. Your palm, I'm assuming this is the right hand here, is going to show the direction of the force. So the force in this case would be into the screen. Now I'm going to do a quick little example for you. A proton having a speed of 5 times 10 to the 6 meters per second in a magnetic field feels a force of 8 times 10 to the negative 14 newtons toward the west when it moves vertically upward. When moving horizontally in a northerly direction, it feels a force of 0. Determine the magnitude and direction of the magnetic field in this region. Well, the first thing I gotta say is if it's feeling no force as it moves in a northerly direction, I'm going to underline that real quick, that must mean that the magnetic field is either from south to north or north to south, because if you recall, if the movement of the charge is parallel to the field lines, you get 0 force. So we know that it has to be either north to south or south to north. So let's go ahead and write our formula. Force equals charge times velocity times b times the sine of theta. Now, I can kind of get rid of the sine of theta right away because we know that this is at a right angle to the field. If it's moving directly vertically upward, that's at a right angle to that other axis. So I'm just going to say that this is the sine of 90, and we'll get rid of that right off the bat. And we're solving this for the magnitude of the magnetic field. And so we will make that F over QV. Now we can put some numbers in here. 8 times 10 to the negative 14 newtons. And it's a proton, so it's going to be 1.6 times 10 to the negative 19 coulombs of charge. And we had a speed of 5 times 10 to the 6 meters per second. And that's going to come out to 0.10 Tesla. Now the question is, what is the direction here? Now what I'm going to do here is, I know when it's moving vertically upward that the force is towards the west. So I'm going to imagine that I have a map here, and I've got north, south, east, and west. So I know that the force is to the west when it's moving vertically upward, which in this scenario would be out of the page. So if I take my thumb and point it out of the page and orient my palm so it's to the west, or in this case to the left, I notice that all my fingers are pointing up, which is to the north. So now I know that my magnetic field is 0.10 Tesla north. One of the consequences of charged particles moving freely in a magnetic field is that the force that is felt by those charges will always be perpendicular to the velocity of the charge. We've encountered this situation before. One of the situations we encountered this before was orbit. And we would have a satellite that was orbiting the Earth in a circular path, and the force was always pointed towards the center of the Earth. In that case, the force was always perpendicular to the velocity. Well, it turns out if you have a force that's always perpendicular to the velocity, things move in circles. And this force becomes a centripetal force. I'm going to write a little b here for magnetic force. And it's a centripetal force. Now, again, we know that centripetal forces, this magnetic force, is equal to mv squared over r. How do I know that? Well, that's because I remember what we did last semester. when we learned about centripetal force. What that means is that this magnetic force equals the mass times v squared over r, but the magnetic force we just learned in this situation is QVB. So we have QVB equals mv squared over r. And what I see here is that one of these velocities is going to cancel. And if I solve this for the radius of the circle that this thing would move in, I get that the radius equals mv over qb. You may notice that mv is the momentum of this particle. So the more momentum it has, the bigger the radius of curvature. That kind of makes sense. Remember, momentum is kind of it's inertia. It's the tendency to want to go straight. And so more of that would make us want to have a bigger radius of curvature. QB is the two things that basically determine the size of the force, which is going to pull it into a tighter radius. So to me, this makes a lot of sense. Let's use this in an example. An electron travels at 2 × 10⁷ meters per second in a plane perpendicular to a uniform 0.010 Tesla magnetic field. Determine the radius of curvature of the electron's path. Essentially what we're going to do here is we're going to just plug numbers into this equation. That's essentially all you ever do with this equation, is solve it for one of the variables and plug it in. So I've got R equals mv over qb. So the mass of an electron, 9.11 times 10 to the negative 31 kilograms. The velocity, 2 × 10⁷ meters per second. The charge of an electron is 1.6 × 10 to the negative 19 coulombs. You notice I didn't put the negative in there. The negative is just direction, and we weren't asked to find that in this case. And what else? The B field is 0.010 Tesla. Plugging that into a calculator is going to give you 0.011 meters or 1.1 centimeters. Okay, that's about all you do with these things.